Today we will start chapter 6, which is dedicated to the application of the definite integrals. So in the previous lectures we already have studied about the um, integration of the continuous function as the definite as well as to the indefinite integrals. Moreover, we also have studied about the Riemann sums for the function, and we proved that we could evaluate the definite integrals using the fundamental theorem of calculus. We also found in the previous chapter that the area under the curve and the area between the two curves could be defined and computed as a definite integral. Now, in this chapter, which is the chapter 6, which is specially devoted to the application of the definite integrals. So, in this chapter, we extend the application of the definite integrals to the defining and finding the volumes, lengths of the plane curves, and the areas of the surfaces of the revolution. So, so basically, our main aim is to find the volumes that is covered by the solids, length of the plane curves, and the area of the surfaces of the revolution. So later on, with the passage of time, I will define you how we can find the volume, length of the plane curves, and the area of the surfaces of the revolution. So before going to move on, I would like to start from the volumes, how to compute the volumes using the cross sections. So basically, we define the volume of solid by using the areas of the cross section. A cross section of the solid S, which can be defined like, for instance, if we have this solid, you see, this solid is lying on the x and y axis. If I consider onto the cross-section area onto the uh, x-axis, you see there is a plane. We call it as a p of x, which is cut, which does cut this solid by the point x. So the length of this solid is starting from the point A and ending up to the point B, and this blue plane is cut by this solid, and this area is basically the area of the cross section, and this will be our point of interest, and we call it as the area of cross section. So our idea is basically to compute the volume. So volume can be easily computed by the volume V is equal to the area times the height. So the next question is how we can extract the area and the height from this solid. For this, we have extracted this cross-section area into the new figures, which is this one. So basically this is any arbitrary figure. So the area base, of course, when we talk about the volume, we will always have the base area. So this is called basically the base area of the plane region whose area we know. And this is the height of the cylindrical solid region, and we can easily compute the volume by the base area times its height. So this is the base area, this one. We can say like the lower one, this is the base area. And the height, which is defined by this variable h. So the cylindrical solid based on the region, the volume is defined by the base area times its height. So the volume in this case, we can say that the volume can be defined like the area. Now the area is basically the base area times its height. So basically, if you come up to the main figure, if we have the 2 points over here and it is cut by the two vertical planes, the one is this one and let us say we're starting from this a, maybe any variable x k minus 1, and if this is the xk. So in this case, the lower one is xk minus 1, and the above one is the xk. So the distance between them would become the height, and the area would be is simply called the base area. So in that manner, we can easily compute the area, which is represented by a times its height. This is how we can compute the volume. This is the volume of a cylindrical solid is always defined to be its base area times its height. Now we calculate the volume of solid by the definite integral of the cross-sectional area A of x, and we show how this integral is obtained by method of slicing. So first we will use the method of the slicing. The method of slicing is nothing but is represented by this figure, like we have done before. If I have the plane over here, if the plane cut this figure from here, from xk minus 1 to the xk, this area is basically called the method of slicing. So here we will start from the method of slicing. I will use the same figure that we have used before. There was a solid that was ranging from the point A to the B, and in between them, and it was of course lying on the x-axis. If we have the A, let me call this is starting point is x naught, and similarly x1, x2, x3 up to xk minus 1, xk, and this is still moving on up to the xn minus 1, and to the uh, B point is xn. So within that we have infinitely many intervals. So A is of course x naught, which is larger, x1 is larger, of course x2 is larger, and still going on up to the xk minus 1, and to the xk, and still going on up to the xn minus 1, and xn is larger than xn minus 1, which is equivalent to the b. So in shorter words, we can say that A is equal to the x naught and B is equal to the xn. So A is starting point with is starting with the length of the volume solid is starting. So of course you see that here the shape is changing as x is growing. You see x is going from 0 to x, and within that x is changing is A to B. So the shape is moving drastically. So the point is that we will draw our two perpendicular plane in this solid. So the one is perpendicular plane is lying on the xk minus 1, which is represented by this blue lines, and the other plane is represented by the xk. So if the two planes are here, if let me call this is a P1, which is a plane 1, and this is a plane 2. So if I extract this area or this cross section into the new figure, which is this one, so the xk minus 1 is here and the xk is here. Of course, if xk minus xk minus 1, this will have some width, which is this one, and this width is represented by the delta k, and the delta k is delta xk is simply the final xk minus the initial xk minus 1. So this is the only the cylindrical base, approximate cylindrical base, or the width is only of the one loaf or the one slice, but we have to compute the all of them. So for this we will approach all this case to the infinity. So at the moment we have the volume of the kth slab, which is approximately Vk is is equal to the area of the cross section, which is the depending on, of course, solely on xk, and to the width delta xk. So we already computed the delta xk, which is the width of this one. Now the cross section area is basically this. This is the cross section area. So the cross section area, which is, I would say that A of xk multiplied by the width. So this is how we can compute the volume. But this is the this is the volume of the kth slab. But as I said, I want to compute the volume of the whole solid. For this, I would say that the volume approximately equivalent to k is starting from 1 to n. So as I said, there are n uh, between A to B. The n is discretized n times. So from A to N, sorry, K is from 1 to N, and the volume Vk of this, the same volume, which is equivalent to this. K is starting from 1 to N, and we know the volume, which is the A of xk and delta of xk, which is the A of xk times delta of xk, and of course A of xk is the cross-sectional area, and the delta of xk is the width. Now, here we will apply the theory of the Riemann sum for the function a of x. So we know that a of x is on the interval a to b, because if you see this cross-section area is starting from a and ending up to the point b. So we expect the approximation from these sum to improve the norm of the partition of the interval ab, which must goes to 0. Taking a partition AB on the nth subinterval, we can say that the norm of P must goes to 0. So for this, we can have like the limit, which is the crucial part. The limit n goes to infinity, taking by this sum, which is this. Basically, I'm treating this sum. K is starting from 1 to n, A of xk and to the delta of xk, which is equal to A to B and to the cross-sectional area A of x is this one, and the delta xk, which is the width, has turned into the differential, which is dx. So we can define the limiting value, limiting definite integral to the Riemann sum by the volume of the solid S. So basically, this is the Riemann sum and this is our definite integral. And this definition is defined by the following, defined like this. The volume of solid of integrable cross-section area A of x from the point x is equal to A to the point x is equal to B. If I consider this part like here, you see, starting from x is equal to A and ending up to the point x is equal to B is the integral of the A from A to B. So A to B, A of x is the cross-section area and D of x is the differential. So this is how we can compute the volume by using the slicing method. So basically we have sliced the whole, one part of the whole solid, and we said that of these small segments are going to infinite, so there are infinitely many slices are here. So this is method is valid for the Riemann sums, but of course the Riemann sums are equivalent to the some definite integrals. So we have transformed Riemann sums into the definite integrals. But in the further questions, we will use this definite integrals to use the area of to use the volume of the solid. Here I will start a question of the pyramid. In this question, he wants to compute the volume of the pyramid. Let us read the question. In the question, he's saying that a pyramid 3 meter high has a square base that is 3 meter on a side. The cross section of the pyramid perpendicular to the altitude x meter down from the vertex is a squared x meter on a side. Find the volume of the pyramid. So first, let us draw the figure. The figure is this. In this figure is basically the main caricature of the this example. So the pyramid 3 meter high. So the parameter is the 3 meter high, and the base is a 3 meter on the side. So base is of course the 3 meter on the each side. You see this one starting from 0 to 3, and the base is also 3 meter high. The cross section of the pyramid perpendicular to the altitude. You see the cross section is basically which is represented by this x. This is the typical cross section. Basically this is the plane that is cutting the pyramid. Of course all the sides are same. This has the side x. So basically we have to compute the volume. So in order to compute the volume, first we have to draw the pyramid. We already drawn. Secondly, we have to find the area of the cross section. So the area of this cross section in this case, so basically let us start from the solution. The solution says, so we have to find this area of the cross section. So basically this is the squared, this one, by the two sides. Each side is x meter, x meter, x and x. And if I want to compute the area, so which is simply a of x, so which is the length time width, this is the x times x, which is equivalent to the x squared. So we have computed that our cross section is x squared. Now the next one is to find the limit of integration. So you see this pyramid is about the x-axis, which is starting from 0 and ending up to the point 3. So we can say that our lower limit, which is we can call this is a cross section. The one is cross section. The second is limit of integration. So the lower limit is starting from x is equal to 0 and it is finishing up to the x is equal to 3. So this is covered this whole line from 0 to 3. So we have found the limit of integration as well as to the cross-sectional area. Now the third step is you have to evaluate this integral. So the volume V is equivalent to the starting from A to B, right? And the cross-section area A of x dx. And then, now the lower limit is equivalent to, of course, this is equivalent to A. Of course, this is equivalent to B. This is starting from 0 to 3. The cross-section area is x squared and dx. And you can here easily evaluate this integral, which is of course a definite integral. The antiderivative exists. The x cubed by 3, and this is 0 to 3, and all together this will become to the by 3 is a 9 is a 9 meter cube. So this is the volume of this pyramid, which is ranging from 0 to 3. So let us start from another question. Uh, in this question, he want to compute the volume of the wedge. The wedge is given like a curved wedge is cut from the circular cylinder of the radius 3 by two planes. The one plane is perpendicular to the x-axis of the cylinder. The second plane crosses the first plane at 45-degree angle at the center of the cylinder. So we have to find the volume of the wedge. So the wedge is like this, right? So let us start from the question. In the question, a curved wedge is cut from the circular cylinder. So we have the knowledge of the equation of the cylinder, which is the x squared plus y squared is equal to the a squared cylindrical shape. So in this case, we have a is equal to 3. So x squared plus y squared is equal to 3 squared, which is, of course, you can call it 9. Or in other words, you can say that x squared plus y squared is equal to 9. By the two planes, the one plane is perpendicular to the x-axis of the cylinder. So this is basically the cylinder, and the one plane which is represented by this purple color, uh, which you see that this is the plane which is perpendicular to the x-axis, where I'm putting some dots. This plane is perpendicular to the x-axis. This is the first plane. You can call it as a, maybe you can call it as a P1, right? And the other plane, which is called second plane, crosses the first plane at the angle of 45 degree from the center of the cylinder. So basically this is the plane. Let me change the color. This is the plane which is cut by this cylinder at the 45 degree angle. So the first plane is this, and the second plane is passing by this 45-degree angle, which is called the P2. So P1 and the P2, they are two planes. So all together, this is called the wedge-like shape that is that is cutting from this side like this one. So the P2 is responsible for the wedge-like shape of the cylinder. Now, we have already given of the radius of the cylinder. The cylinder is moving from 0 to 3. So this is the radius of the cylinder from 0 to 3. So one can say that the radius of the cylinder is r is equal to 3. Now we have the knowledge of the equation of the cylinder. So in that case, I will use this equation star, let's say. So we know that this cross section is, this has the length, or you can say the height in length x, but we want to confirm the sides of the y. So in that case, I will simply say that I will solve this equation in terms of y. So I will simply get, let us write first x squared plus y squared is equal to 9. So for the y is equal to 9 minus x squared whole root, and this is the plus minus. So since this is the y negative side, so we have the y is equal to plus 9 minus x squared, and y is equal to minus of 9 minus x squared. So the minus side is here. So this point is x, which is the, of course, x is in a straight line, and the y is appearing like minus root of 9 minus x squared, and this side is basically the x comma plus root of 9 minus x squared. So basically we have to find the cross section in order to compute the volume of the solid, volume of the wedge. So now let us work from the area of the cross section. So the area of the cross section, which is A of x, is basically the height time its width. So the height, if you look at this figure, so since it is occupying on the x-axis and the y-axis, so, and the information of the x-axis is from 0 to 3, so it is moving like a straight line. So the height would be the x, and the width, so basically this is the width. The width, it's like the height is represented by this x. Of course we are working into the three-dimensional figures. The height is this and the width is this one. If I separate this one, you can see this is the height x, and this is the width. So half of the 9 minus x square root here, from this to this, and half of the 9 minus x square root is here. So altogether this is the twice of root 9 minus x square. So the width is basically will become like twice of 9 minus x squared. So altogether we can say that this is the 2x root of 9 minus x squared. So this is basically called the cross-sectional area. So once we know the cross-sectional area and we also know the limit of integration, because which are very simple, which is moving from 0 to this 3. So this is called this is the cross-sectional area, and the limits are basically a is equal to 0 and b is equal to 3, and the integral will become like from the volume is equal to from a to b, the area of the cross section A of x dx is equal to from 0 to 3, the area of the cross section is 2x root of 9 minus x squared dx, and you can easily solve by the substitution, which is the substitution will become like, we can call it as a u is equal to 9 minus x squared, and the du will become minus 2x dx, and from here dx is equal to du by 2x with some minus, and now the limit of integration is become, after substituting, if you substitute this one, this will become 9 minus x squared, 9 minus x square root, and this will cancel out, and all together you will get the answer 18. So I'm not solving the integral because we already solved in the previous chapter. So the volume is 18. This one. Now I will move to the solids of the revolution. In the more decent way, we can call it as a disk method. So the disk method is basically the solid generated by the rotating or revolving a plane region about the x-axis in its plane. It's called the solid of revolution. So find the volume like we have shown into the figure, this one, we need only to observe the cross-section area A of x of the disk radius r of x that appears into the distance of the present region's boundary from the axis of the revolution. The area is then, so basically the area of the or you can say the cross-section area A of x in this case has to be pi r square, and this is the pi is the and the radius is r is basically the radius is squared, and in that case of course radius is in terms of r of x. I will explain to you why we are calling it as a r of x square. So, let us start from the very simple example. If you have a curve of the y is equal to root of x, and which is of course this is the of course by represented by this blue line, this one, this dotted blue line, and if you rotate this curve anti-clockwise around the x-axis, so if you rotate this curve anti-clockwise around the x-axis, like this, and also from here is this, so you will automatically get this shape. So basically you have to rotate this curve y is equal to root x into the anti-clockwise direction, and you will form the solid. Now in order to form the solid, you will put a disk over there. You see in the golden color there is a disk. This is why we are calling it as a disk method, and this disk is not basically fixed at the point at this point. This is moving from uh, the interval from 0 to the interval to the 4. So as it goes close to 0, the size of the disk will getting smaller and smaller. At is on the other side, as it grows to the 4, the size of the disk will getting larger and to the larger. We only need to cater this one, which is radius. So of course the radius is here is basically the root of x, which is the value of the function. Also it is clearly indicated that from here to the boundary, which is the interval root of which is the function root of x. So basically as x is getting larger and larger, this will grow more and more. This is why we are calling it as a radius. So if he want to compute the volume of this solid, we can easily compute the volume of this solid by the formulation which is given by this equation. Let me call this is the equation 1, and if we want to compute the volume of the solid, so that we as we see from the figure, this is starting from 0 and ending up to the 0.4. We only have to use this volume V A starting from 0 and ending up to the 4, and to the cross-section area A of x. So the A of x can be easily determined by, as I said, that this is basically the height or the radius, you can say that, of this solid. So of course this is the same because we have rotate along the x-axis over here, and this is formed the solid. So basically this is the radius, which is the root of x. So we can write it here over as 0 to 4, and this area was pi, cross-section area, which is represented by this definition pi r of x, and the r of x is in our case is the root of x squared dx. Or we can say that r of x is equal to the root of x. So basically this is the radius. So whenever we solve this, we can have pi of 0 to 4 x dx, and this will simply gives us the x squared by 2, 0 to 4, and you further evolve this limit of integration, you will get the answer like pi of course 4 square divided by 2, and because of this is all 0, is equal to the 8 pi. So the volume covered by this solid is 8 pi. In this question, we also have to compute the volume of the solid generated by the revolving the region bounded by the curve, which is y is equal to root of x, and the lines y is equal to 1, x is equal to 4 about the line y is equal to 1. So basically the question is the same as the previous one, but there is a twist in this question. Let us start from the sketching the figure. This one, this one. So first we have to find the region, first we have to look for the region which is bounded by the curve y is equal to root x, which is this. This is the curve y is equal to the root x. But on the same time, he's saying that the region bounded by the curve this and the lines y is equal to 1. So the y is equal to 1 line is somewhere here. Y is equal to 1. So this is bounded by this, and up to x is equal to 4. So this is of course x-axis, this is 4. We can call it 3. This is 2, and this is 1. Okay. This one. So basically we have to find this area while rotating along the line y is equal to 1. So if we rotate this curve around along the y-axis, we will have this one. So we have the area like this, solid. So we all together we have this area. Now we know that this curve is y is equal to root of x, but in order to compute the volume, we know that volume is equal to a to b a of x dx. Since we are using the disk method, so this has become a to b pi the radius r of x square, which is basically the pi r square dx. So here we have to compute the r of x. So for the sake of your better understanding, I have copied the figure from the book, and which says this. So basically this was the same figure that has transformed from here to here. So that is y is equal to 1. So this curve y is equal to root of x has moved along the line y is equal to 1. Now we have to find this r of x. Now this r of x you see over here. Now this is not moving about the origin. So it was moving about the line y is equal to 1. So and we have to find the area not from this region. No, we have to find the area from here. Maybe I use a different color, from 1 to 4. So the radius r of x, which is the root of x, which is represented by the curve, minus this one, because this is not included. This part is not included. This is a unit area. So one can say that the r of x is the root of x minus 1, this one. So this is not included. So we can also say, like, from the equation, because how we have computed this x, because if you put um, y is equal to 1 over here, so you can simply say that x is equal to 1. Now we'll substitute into the question, and this will comes like the volume. It is moving from 1 to 4. So the lower limit is 1, upper limit is 4. The pi as it, maybe we can put outside pi, and the r of x, which is the root of x minus 1 whole squared, because of this formulation, dx. And once you solve this one, you will get the answer 7 pi. After some integration, you will have the 7 pi by 6. So the main idea in this question was how to compute this radius. So as demanded by the question was saying that the region bounded by the curve y is equal to root x and the lines y is equal to 1, which was this dotted line, you can say this solid line over here, up to x is equal to 4, which is this one, x is equal to 4, which is this one, and about the line y is equal to 1. So this was rotating like here. So we put the disk inside the solid, and we start from 1 and up to 4, and for the radius we have the curve minus this region, because this was not included. So we have said that our radius r is equal to root of x minus 1, because this is starting from here, and this is how we can find the answer. So for the for the sake of time, I'm not computing the this very trivial integral. You can easily compute by the simple manipulations. And moreover, there's a one thing I would like to say, that in these computation, these were the revolution about the x-axis. You see, the curve was moving along the x-axis. Now I'm going to tell you about if there is a revolution about the y-axis. So the revolution, the rough idea about the revolution about the y-axis, for instance, you have any x and y-axis, and you have any curve like this. So if you rotate along the y-axis, so this will become x and y. You have to rotate about the y-axis. So this will become like moving this and this one. So this is a rotation about the y-axis. I am giving you the proper definition, and then I will move to the question. So basically, these are the terminologies when we have to find the volume of the solid, and the solid is solid has a revolution along the y-axis. Previously we have studied about the when the solid has a revolution around the x-axis. So in this case we only have the change of variable from x to y. So now the cross-section area will compute it in terms of y, and the limit of integration from a to b, rather than we have over here from c to d. And of course here we will find the radius in terms of y. So this is the formulation for the volume by the disk for the rotation about the y-axis. So everything is same like before, but here we only have to change the axis from x to y, because the revolution of the solid or the of this curve along the y-axis. So for this I have chosen this question. In this question we have to again find the volume, and the volume of the solid, and this solid is basically generated by the function x is equal to 2 by y, and this is ranging between 1 to 4. So basically if you read the question, in this question he's saying that find the volume of the solid generated by revolving the region between the x-axis, sorry, between the y-axis and the curve x is equal to 2 by y, and the y is ranging between 1 to 4 about the y-axis. This is the crucial thing. So now this one is basically revolving about the y-axis. So this is the curve which is the x is equal to 2 by y, which is the curve basically x is equal to 2 by y, and this is moving like this. If you rotate this curve along the y-axis, you will have this formation. So this is basically moving from 1 to 4, and this has the curve y is equal to 2 by y. So of course order to pair is written in terms of x comma y. So of course the x is 2 comma y and the y is this one, and within this region or this solid you have to put a solid disk, because we are working for the or working by the disk method. So this disk can go up with the smaller values of y. This can go down with the larger values of y's. So, but of course this cannot go beyond the limits of the 1 and to the 4. So the first point was to compute the limit of the first point is to compute the sketch the graphs. So we have sketched the graph. Now the point is we have to find the cross section area. The cross section area is basically this r of y, this area, cross section area, this one, from here to here, because this is moving all along the y-axis. So the cross section area r of y is basically 2 by y, from here to here. This is the cross section area 2 by y. Now the limit of integration is very simple, which is given like y is ranging between 1 and to the 4. So we can easily substitute into the formulation of the volume, which is c to d pi of r of y whole squared dy, and this pi is as it the c to d. So basically this is this your c, and the d is this one. So starting from 1 and up to the 4, and r of y is already computed. This was the 2 over y, which is a 2 by y whole squared of the dy. So if you evaluate this one, you will get like 1 to 4. This is the 2 is a 4 is the 4 over here, and the y 1 over y squared dy, and all together see the 4 pi of, because this y goes up, y minus 2, and all together this will become I'm just going to write the direct limits, 3 by 4, and all together you will get the answer 3 pi. So the volume of this solid from 1 to 4 is 3 pi. So in this case this was a revolution about the y-axis but not along the x-axis, and this we have find the area of the cross section, or you can say the radius of this disk, and we substituted into our integral in the definite integral, because we have known the limit of integration, and we solved it and find the volume of this solid. And moreover, we have finished the method of the slicing disk method about the x-axis, about the y-axis. I recommend you to the some questions which are from the exercise 6.1 of the book Thomas, and the questions are 19, 22, 25, 26, 28, and the question 31, 34, 36, and this is enough. So you can practice this question of the exercise 6.1. Thank you.